Let's look at exercise 8-01, direct proportion. Questions 7 through 10. Question 7. K varies directly with L. If L is 9.5 when K equals 1045, what is the value of K when L is 1.65? Select A, B, C, or D. Okay, so we follow what the examples in the book have shown us. We put an equation down. We've got L equals a constant times K. I've got a small k here and the large K. Okay, so that implies that the small k equals L divided by the large K. We're given that information. We've got 9.5, and we've got this one here, 1045, and we get K equals 0.0090909, and then I think it's 0.091. Therefore, L equals, that's the constant, times K. Okay, we just substitute the value that we found for K in there. Now they ask us here, what is the value of K when L is 1.65? Well, when L is 1.65, K is 1.65 divided by our constant, and that's 181.5. And if we look at the answer choices, it's C. So the answer choice C is correct. 8. A linear relationship exists between the mass of a car m kilograms and its fuel consumption rate F in litres per 100 kilometres. A. Find the variation equation for F if a 1,000 kilogram car uses fuel at a rate of 6 litres per 100 kilometres. Okay, it's a linear relationship between the mass of a car, so I've put mass on the x-axis, and its fuel consumption rate, which is litres per 100 kilometres. Now they tell us it's linear, so we can draw it like that. Okay, as the mass goes up, the number of litres per 100 kilometres would go up. So we're looking for the gradient. Now the gradient is the rise over the run. The rise is 6 litres per 100 kilometres, so at the y-axis, so it's 6. And we know the run is 1,000 kilograms. So the gradient's going to be the rise, which is 6 divided by 1,000. Therefore, F is equal to 6 over 1,000 times M. B, find the fuel consumption of a 2,500 kilogram car. We're going to use this. Okay, so we've got F equals 6 over 1,000 times M. That's 2,500, 2,500 there. And so that resolves itself to 15 litres per 100 kilometres. 9. For an object that is cooling, the drop in temperature varies directly with time. If the temperature drops 8 degrees C in 5 minutes, how long would it take to drop 10 degrees C? Select the correct answer, A, B, C, or D. Okay, so I've drawn this. We've got the temperature up here and the time. Now it's dropping because as the time increases, it's cooling. Okay, the gradient here is -8 on 5 because the drop in temperature is -8. And the time is 5 minutes, within 5 minutes. So the rise, in this case, the fall is -8 and over 5, because in the positive direction it's 5 minutes. So we have T equals -8 on 5 times time, small t, so it's temperature here and that one. Now it says here, how long would it take to drop 10 degrees? Now that says drop 10 degrees, so that in fact would be -10. So what I put in here, when I substituted it in, we've got T, I made T the subject, so it's 5 times the temperature divided by -8. And remember, it had to drop 10 degrees, so I've got -10 times 5 divided by -8, and that's 6.25 minutes. Well, it has to be a positive number, so we couldn't have -6.25 minutes, okay? So it's 6.25 minutes, and up here we get to see that as A, so therefore answer choice A is correct. 10. The weight of an astronaut on Mars is proportional to his weight on Earth. A 72 kilogram astronaut weighs 27.4 kilograms on Mars, so he's going to weigh less on Mars. So keep that in mind, so when you do get an answer, you can double check to make sure it makes sense. A. Calculate how much a 60 kilogram astronaut weighs on Mars, correct to 1 decimal place. So when they said 60 kilogram astronaut, that means on Earth. How much does that person weigh on Mars? Okay, we're expecting that person to weigh less than 60 kilograms. And it says to 1 decimal place. So we've got the weight on Earth equals K times the weight on M. Therefore, K equals the weight on Earth divided by the weight on Mars. Now, I've given an example. 72 kilogram astronaut on Earth is 27.4 on Mars. So we've got our constant here of 2.62774. We can rewrite the equation now substituting this for K, we've got the weight on Earth equals 2.62774, the weight on Mars. The question was, it's 60 kilogram astronaut on Earth, how much does he weigh on Mars? So we've got weight on Mars, so we'll see we'll change this again, is equal to weight on the Earth divided by the constant, and that's 22.8 kilograms to 1 decimal place. B, if an astronaut weighs 32 kilograms on Mars, calculate his weight on Earth, correct, to 1 decimal place. So we're expecting the number to be larger than 32. So the weight on Earth, we go back to this one, equals 2.62774 times, we've been told what the weight is on Mars is 32, and that's 84.1 kilogram to 1 decimal place.